So today we are talking about general theory of relativity. We all know that it became relevant that Einstein figured out it by considering light as a constant. So light is a constant. Light is a constant. So he then realized that by taking light constant, he can see that there is a change in space and time. So there is no absolute value for any space and time. So space and time are related to each other. So but considering that you know all these things, I might just jump into the general theory of relativity because it's more clear. So, general theory of relativity just says that there is no gravity. According to Newton, there is a gravitational force between two objects, but Einstein thought that okay, light travels, so light has to have some mass, at least in a theory, so it should bend. So he taken an elevator and consider there is a coordinate system attached to this elevator and there is a man here and there is another coordinate system attached to earth and there is a man standing on the earth and there is another coordinate system attached to the earth. So if this elevator is freely falling, that means the elevator is falling at a rate of g when it is at the nearest to the earth's surface, then this guy wouldn't feel any force. This guy would see that uh, there is no information about what's happening on the other side of this elevator walls. So this guy says, okay, there is no gravity because I'm feeling no force. So this guy would say that no gravitational force, and this guy will say that wait a second, there is a gravitational force, but you are freely falling in the gravitational force. You wouldn't feel that force, but this guy wouldn't agree until he gets out. So this guy would say there is a gravitational force, there is a gravitational force, and there is not a gravitational force. So these both would disagree. If there is I don't know, a secret telephone that these two guys are transmitting information without knowing what's happening inside and without knowing what's happening outside for this guy and this guy. So Einstein thought that maybe both are right or wrong in some other way. Both are true and false in the same way. So Einstein thought that okay, I would construct a principle where there should not be anything which is disagreeing with this both figures. So he said that I would introduce a coordinate system which is both true for both these guys. So he said that, and if this is an earth and this is the lift, I would pick up a coordinate system where both guys would see the coordinate system because both guys are attached to the same coordinate system which Einstein has then derived. And this coordinate system has two components, which is space and time. And space itself has three components. I mean, at that time, not now, because string theory has developed and we have more spatial dimensions. But at that time, space has only three components, and time has only one component. I will get to that. So he said that, okay, what if I create a space-time here in the vicinity of this elevator, and I would say that the space is bent so that he could see that the bent space and the elevator, as we've taken in the previous case, the elevator is freely falling. He would say that the space itself is curved so that the elevator is actually moving with respect to the space-time which is given by Einstein. So the space-time is itself bent because the elevator is freely falling. Now in this case, both would say that no, there is no freely falling. I'm just going in a straight line or maybe another path so that the elevator starts to move as if there was a freely falling situation for this guy in the other situation. I mean, in the previous one. So he would say that the elevator would would travel into a curved space-time. So when it is transferred into the original coordinate system as the Newtonian coordinate system, this would feel like a free fall. And when we get closer to the surface of the earth, and as we're taken to the previous observation, this free fall, it should have more acceleration as compared to this acceleration when it is seen from this guy attached to a Newtonian coordinate system in the previous case. But here you can see that there is no Newtonian coordinate system. There is actually a curved coordinate system which applies to both these persons. So he would say that the curvature is more here, which means that actually the curvature is more here. The path traveled would take less time to travel an equal distances as compared to here. So he would say that there is a coordinate system which is linked to here. If this is one and this is two parts of the space, these two parts linked with a single coordinate system where the curvature is less here and curvature is more here. So we can extend it to every part of the space. And if this is moon or its sun or whatever it may be, and he would create a coordinate system where the curvature depends on the spatial coordinate system, which it has spatial and time coordinate system, which is connected to this energy ball, which is nothing but sun in this example, or any other energy ball, because energy is nothing but mass, as Einstein already derived E is equals to mc square, or I would say that m is equals to E by c square, which is originally returned. So I would say that this energy creates a curvature in space-time, which is related to the coordinate system, and will give us mu g mu nu, which mu is actually a tensor, not a vector. So the curvature is actually might be a tensor or might be a scalar if we compress this. I mean, if we take out each coordinates, take out each axis of the coordinate system. So anyway, if there is no mass, the curvature would be zero. I want to take r equals 0, and if there's any mass, the curvature is there, and it is some constant, some k, depends on the vicinity of the surface, vicinity of the mass or energy present here. So he already know that mass can be derived in terms of the momentum. So energy momentum tensor, it is given by T mu nu, and G mu nu and T mu nu, which is G mu nu is just the spatial coordinates, and T mu nu is just the energy momentum tensor, and these two are related by some constant. I don't know how we derived it, but 8 pi g is the constant. So this is the equation. Sorry, 8 pi g comes over here. 8 pi g T mu nu. So this is the thing that he derived. 8 pi g T mu nu is equal to T mu nu. So in summary, then I would say that for any mass or for any energy that is traveling, it would have a curvature. See, energy can not be visualized. So I would say that if this is a space, this is a space-time, and these are the curvature of the space-time. If you get really confused, you can put so many elevators here, so that the path for the elevator would be the path of geodesic inside. It means the shortest path in this radius. So if we put all of these little elevators here, and we pick up a coordinate system where each elevator has its own sense of space and its own sense of time, which is derived by the special theory of relativity. And here it's so simple because as the curvature is more, the elevator would travel much more speed, and the curvature is less, elevator would travel a less speed. So even if there is no energy here, and if there is a curvature, we would sense that the energy is there, but we are not seeing it. So that is momentum tensor. I would say momentum tensor T mu nu, and it's related by G mu nu, which is the curvature here. Which is the spatial coordinate here, and which also we can transfer it to R mu nu, which is the curvature itself. So R mu nu is related to T mu nu by this coordinate system, which is easy to pick because you have no visualization of this 4-dimensional space, because we already have 3-dimensional space and we cannot expect another dimension to put to that, especially time. So I would say that there is a way, and this way I put is I have to put little elevators down here so that the elevator is freely falling in Newtonian frame, but are connected to each other to bring out a universal frame, which is nothing but a Einsteinian frame or general relativity, whatever the frame it is, but it's curved. So here we see there is no mass, but the energy is traveling. So this is an example for a gravitational wave, because this is travels in this direction, and this curvature is transferred from one part to the other part. This is a gravitational wave. So it can be occurred by a disturbance in mass. So if there is sun here, and if there is moon here, there is much more gravitational force here, and as this goes by, the gravitational force becomes less and less, similarly to the Earth. And this Earth is affected by the curvature of space-time here. So this Earth can itself meant to be as a big elevator, so that this elevator is actually moving in a free fall for this moon, affected by this moon. He predicted a coordinate system for both Earth and Sun, and for whole the space around here with a curved coordinate system, and he called it as a space-time coordinate system. And there's so many scientists who decided to put them together to actually see the path of the orbits of so many things, Mercury or whatever it may be, path of the orbits, which is not actually measured by Newtonian times, and now it is measured and it's actually quite true. And what I'm going to say is that if you feel like I'm sitting here, right, and I feel that there is a gravitational force, actually, if I'm sitting here and I would take the Einsteinian frame, I would take myself as an elevator, I'm freely falling, which means that the Earth is actually coming upwards. So you don't see Earth actually coming upwards. It means that the space-time itself is bent for my frame, which is, I would say, my elevator. I'm the elevator, and space-time is bent. So I'm actually bent. So the time as I go by, there is a moment from passing from time to time, and I'm standing here with a space-time bent, because I'm close to Earth. So Kaluza came up with another idea, so he could pick up another coordinate system, actually spatial coordinate system. To pick up a spatial coordinate system, he introduced another coordinate system which is curved and which is so small, and he says that when a particle, my subordinate particle, which is traveled in this curved space, would return to this same spatial coordinate, same fourth spatial coordinate. So he said that this is called a cylindrical condition, which means that we know that any of the two spatial coordinate system has to be perpendicular to each other. So he introduced that because the fourth coordinate system has to be independent of another three coordinate system, and the fourth coordinate system has to be in circle, which is a bounded fiber circles. I don't know, because you will get it in string theory. So this is the start of the string theory. And he would say that whatever this is traveling in this circle group is nothing but charge. So in string theory, I already have made a video on what charge is in string theory. So this would be the starting sense of what a charge is. For electromagnetic plus gravitational field, we tried to do it. So I would say that you could pick up a coordinate system here where there is a breakage, and this breakage is linked by this circular coordinate system, and whatever the breakage is, you calculate whatever the field forces or whatever it is. Actually, there is no force here, it's actually a field happening. So he would introduce the electromagnetic field, and along with Einstein, he will combine the electromagnetic field with gravitation, and it form a total electromagnetic gravitational field equations, which is not actually true because he didn't get a charge right. But in string theory, we are going to do some more mathematics to actually visualize what kind of curvatures these extra dimensions have, and to have those extra dimensions for the charge to be same as what is observed in the real world. So that's it for general relativity and the starting of whatever these new coordinate systems have. So that's it.
Okay.